In our today's lesson, we are going to plot the B.M.D as well as the S.F.D for the beam shown in the figure below. This is a continuous beam that is supported on three supports, support A, support B, as well as support C. It is loaded with two loads, a point rod of 3 kilonewtons and a UDL of 1 kilonewtons per meter. Now, we are going to begin with considering span AB. Therefore, consider the span A to B. Now, under span AB, we are going to calculate or to determine the bending moment at point D. This should be point D. We are going to determine the bending moment at point D. And in this case, we are going to use this formula. MD is equals WAB divided by L1. And in this case, this is going to be W, which is the point rod of 3 kilonewtons at D. Therefore, that's going to be 3 multiplied by A, which is 2 meters, multiplied by B, which is 4 meters, distance from D to B. And then we divide by L1. L1 is the span from A to B, which is in total is going to be 6 meters. And this is going to give us a bending moment of 4 kilonewton meter, 4 kNm. Then from there we go to the span BC. The span BC. And in the span BC, we are going to determine the maximum bending moment, which will be given by this formula, WL squared divided by 8. And in this case, W is the UDL of 1 kilonewton per meter. Therefore, that's going to be 1 times the span BC, which is 4 meters. Therefore, 4 squared, we divide this by 8. And this is going to give us a maximum bending moment of 2 kilonewton meter. 2 kilonewton meter. Then after that, we are going to plot the bending moment due to vertical loads. That is due to the load 3 kilonewton and due to the 1 kilonewton per meter UDL. And this is going to be at D. We have a bending moment of 4 kilonewtons. So we are going to approximate it, be at that point, and then we join it to B like that. So the apex of this triangle, we are going to have 4 kilonewton meter. Then the maximum bending moment between B and C is 2 kilonewton meter, approximately that point. And this is going to be a smooth curve, because when we have a UDL, the B.M.D is usually drawn as a smooth curve. Good. Then from there, we are going to determine the area of this bending moment between A and B. And therefore, we go to the same span again, the span AB. So for span AB, A1, that is the area of this bending moment diagram between span A and B, will be given by a half multiplied by the base. A to B, we have a span of 6 meters, multiplied by the height of this triangle, which is 4 units. Therefore, times 4. And that is going to give us 12 square meter. Then we need bar x1. And bar x1 is the distance from the center of gravity of this triangle to point A, or to the end A. Therefore, this is bar x1. Distance from the center of gravity of this triangle all the way to the end A. And that distance will be given by this formula. L1 plus A divided by 3. Why A? Because we are calculating the distance from A to the center of gravity. And this is going to be L1 is 6 meters plus A is 2 meters, and then we divide this by 3. And that is going to give us 2.667, and therefore bar x1 is equals 2.667 meters. Then from there we go to the span B to C. And for the span BC, we are going to calculate the area of this curved surface, and that is A2. A2 will be given by 2/3 of the base. The distance from B to C, or the span B to C, is 4 meters. Therefore, 2/3 of 4 meters multiplied by the height, perpendicular height of this section, which is 2 units, and therefore multiplied that by 2. And that is going to give us an area of 5.333. 5.333 square meters. Then we need bar x2, and bar x2 is the distance from the center of gravity of this section all the way to the end C. Therefore, that is bar x2, and bar x2 of this section will be given by half its base. So bar x2 is going to be half of its base, which is 4 divided by 2, and that's going to give us 2 meters. After that, the next thing will be application of the CLAPEYRON'S equation of 3 moment. And the CLAPEYRON'S equation of 3 moment states that MAL1 plus 2MB into L1 plus L2 plus MCL2 is equal to 6A1 bar x1 divided by L1 plus 6A2 bar x2 divided by L2. So that is how the CLAPEYRON'S equation of 3 moment states. Now, for as a continuous beam with 2 end supports, the bending moment at the end supports, that is bending moment at A as well as bending moment at C, are equal to 0. And therefore, we are going to remain with 2MB, since MAL1 is 0, into bracket L1, which is 6 meters, plus L2, which is 4 meters, plus 0, because MC is 0, being equal to 6 times A1, which is 12 square meters, multiplied by 12, multiplied by bar x1, which is 2.667. We divide this by L1, which is 6 meters, plus 6 multiplied by A2, which is 5.333, multiplied by bar x1, which is 2 meters. Then we divide that by L2, which is the span BC, and that is equal to 4. And therefore, this is going to be 6 plus 4, which is 10. 10 times 2, that is 20. So we are going to have 20 MB being equal to, when we solve this section, it is going to give us 32. That is 6 times 12 times 2.667 divided by 6, that is equal to 32. Plus, the other section is going to give us 16. Therefore, 6 times 5.333 times 2 divided by 4, that is equal to 16. And therefore, the value of the bending moment at B is going to be equal to 32 plus 16, which is 48, 48, we divide by 20. And therefore, the bending moment at B will be given by 48 divided by 20, which is 2.4. And in this case, that bending moment at B is going to be negative, since when the beam bends between A and B, the beam is going to be sagging. Between B and C, it will also be sagging. But at the support B, the beam will, or that bend is going to be a hogging bend. And therefore, when we have a hogging bend, that is usually negative. Then from there, we come at the support B, and we approximate 2.4 units, just some few units above 2 kilonewtons, 2 kilonewton meter, and then we join it at that point. Then we join it at the end C. Then from there, we can shade it like this. We can shade it off, that is the sections that will be denoted by the positive as well as the negative signs, so that they can remain very clear. They can remain very clear. And please, ladies and gentlemen, if you are here and you are yet to subscribe, please remember to do so. Hit the subscription button as well as the notification bell, and we are going to appreciate so very much. This is a positive bending moment. This is a negative bending moment of negative 2.4 kilonewton meter. Negative 2.4 kilonewton meter, and this one is a positive bending moment. Then, after getting the values of the bending moments, the next operation will be reactions calculations, so that they can help us to plot the shear force diagrams. So we go to reactions calculations. Reactions calculations. Reactions calculations. And in this case, we are going to begin with the span BC. So for span BC, we are going to take moments about B. Therefore, taking moments about B, we are going to get the following. So we get, good. So this is going to be RC multiplied by the distance from C to B. That is an anti-clockwise moment, and therefore we are going to have RC times the distance from C to B, which is 4 meters. Then we add this 2.4 kilonewtons, since it is going to be an anti-clockwise moment when we are taking moments about B. So we add 2.4. We equate that to this clockwise moment. We have a UDL of 1 kilonewton per meter between B and C. And we are going first of all to convert it to a point rod, that is multiplying it by the span, and then it will act at the mid span, and the mid span is at 4/2. Therefore, this is going to be RC times 4 being equal to, this one is going to be 8. And then we take 2.4, the other side of the equal, on the other side of the equal sign, which is going to be minus 2.4. And therefore, the reaction at C is going to be equal to 8 minus 2.4 is 5.6. And then we divide by this 4. And RC is going to give us 1.4 kilonewtons. So that is the reaction at C, 1.4 kilonewtons. Then from there we go to the span AB. So for span AB, taking moments about B as well, therefore taking moments about B, we are going to get the following. Therefore, we get, so this is going to be RA times the distance from A to B, that is a clockwise moment. So RA multiplied by the distance from A to B, which is 6 meters, plus, when we are taking moments about B, the moment at B will be a clockwise moment as well. Therefore, we add 2.4 kilonewtons. That is the bending moment at B, 2.4 kilonewtons. We equate this to this anti-clockwise moment of 3, that is the point rod at D, multiplied by the distance from D to B, which is 4 meters. Therefore, we got 3 times a distance of 4 meters. This is going to be equal to RA times 6, which will be 12 minus 2.4. And RA will be equal to 12 minus 2.4 is 9.6, and then we divide that by 6. And 9.6 divided by 6, that is 1.6 kilonewtons. Therefore, the reaction at A is 1.6 kilonewtons. So we come here at the support A and we write that reaction 1.6 kilonewtons. We are remaining with the reaction at B, and for us to get the reaction at B, we are going to say this, that the sum of all the upward acting forces must be equal to the sum of all the downward acting forces. And therefore, we are going to have this upward acting forces. We have reaction at A plus reaction at B plus reaction at C, which will be equal to the downward acting forces, 3 kilonewtons, the load at D, plus a UDL of 1 kilonewtons. Then we convert it to point rod, that is by multiplying it with its span at which or by which it is distributed. So RA, we have got it as 1.6 kilonewtons. RB, we don't know it yet. RC is 1.4 kilonewtons, is equal to 3 plus 4, which is 7 kilonewtons. And RB will be equal to 7 minus 1.6 plus 1.4 is 3 kilonewtons, which is 4 kilonewtons. Therefore, the reaction at B is 4 kilonewtons, 4 Kn. Good. Then, after getting the value or the values of all the reactions, the next thing or the next operation will be shear force calculations. So we go to SF calculations, and for the shear force calculations, we are going to begin with shear force at C, and the shear force at C will be equal to the reaction at C, which is 1.4 kilonewtons. Therefore, SC is equals 1.4 kilonewtons. Then the shear force between C and B, between C and B, is going to change uniformly. Therefore, it will change uniformly from this 1.4 kilonewtons, the shear force at C, so from 1.4 kilonewtons, and it will change to this 1.4 kilonewtons minus this UDL between C and B. When you convert it to point rod, it is going to be 1 kilonewton per meter times the span over which it is distributed, which is 4 meters, and that is going to be 1.4 minus 4, and that's going to give us negative 2.6 kilonewtons. So we are going to have a uniform change of 1.4 kilonewtons to negative 2.6 kilonewtons between C and B. Then from there we go to shear force at B, and the shear force at B is going to be this negative 2.6 kilonewtons plus the reaction at B, since this is an upward acting force, which is 4 kilonewtons. And therefore, negative 2.6 plus 4, that is 1.4 kilonewtons. So we get 1.4 kilonewtons being the shear force at B. Then from there we go to shear force between B and D. Shear force between B and D. Since the span between B and D is not loaded with any load, the shear force between B and D will be equal or will be the same as the shear force at B, which is 1.4 kilonewtons. So it is also equal to 1.4 kilonewtons. And then finally, we determine the shear force between D and A. And the shear force between D and A will be given by this 1.4 kilonewton shear force minus the point load at D, which is 3 kilonewtons. And 1.4 minus 3, that is negative 1.6 kilonewtons. So guys, after we are done with calculating the value of the shear forces, the next thing will be plotting the shear force diagram. And we are going to begin with the shear force at C, which we had as 1.4 kilonewtons. The positive shear forces will appear above this line, negative shear forces below this line. And if we approximate 1.4 kilonewtons to be at this point, that is going to be where we are having the 1.4 kilonewton shear force. Between B and D, we have a change from 1.4 to negative 2.6. So approximately negative 2.6 at that point. So we are going to drop and connect it there. So here we have negative 2.6 kilonewtons. Shear force at B is 1.4 kilonewtons positive, and therefore we are going to, it is going to be at the same level as the shear force at C. So we have 1.4 kilonewtons being the shear force at B. Shear force between B and D, it is still the same 1.4 kilonewtons, and so we connect the 1.4 kilonewtons to D. So here we also have a shear force of 1.4 kilonewtons. Then finally the shear force between D and A, negative 1.6 kilonewtons, and that is going to be approximately here. And so we finish it in that form. So here we have 1.6 kilonewtons, whereby this is a negative shear force, this one is a positive shear force, this one is a negative shear force, and that is a positive shear force. So that's how we plot the shear force diagram for such a continuous beam. So let's meet in yet another lesson. Thank you very much.